So we'll be doing kinematics today. And one of the things that I talked about last time, which was on Tuesday, is the fact that you have a coordinate system and that eventually you're going to map an object's motion onto that coordinate system. And this is the epiphany that I had. It's that kinematics, which is what the book that we're using, recall that the book we're using is this OpenStax book, OpenStax AP college course textbook. Yes, the moon is tidally locked to the earth. So this is the textbook that we're using. Chapter 2 and 3 is kinematics. Now, I always hated kinematics. I was like, this is the most boring, stupid stuff. I can't believe that we have to learn it. Why do I have to learn this stuff? When am I ever going to use it? Until today. And so here's what I just realized today. And this is based upon what I mentioned last time. So I mentioned last time that we have coordinate systems and that we're going to map what we see on the coordinate systems into our mathematical model, or like what we see in the universe, we need to map it onto a mathematical model, and in order for us to make a description about what's going on that we can calculate using mathematical principles. And what I realized is that kinematics right here, so this is displacement, vectors, acceleration, and stuff like that. Kinematics is the process of mapping what we observe onto a coordinate system. So for decades now, ever since I took high school physics, because I did not like my high school physics class. I got better, but I didn't like my high school physics class. And part of the reason I didn't like my high school physics class is because we did so much stuff in kinematics, and I was like, this is not, I mean, I did it, and it was interesting-ish, but it wasn't like playing in the percussion ensemble or in marching band. So it wasn't quite the same thing. And it didn't strike me as nearly as interesting as once I got into college and was doing other aspects of physics and cosmology and things like that. Until this morning, this is just about a half an hour ago, when I realized that what I said last time about needing to map things onto a coordinate system, that is what kinematics is. Kinematics is the process that we go through to take what we observe and to put it on a coordinate system, which means this is the translation process. How do you translate what we observe into an equation that we can then manipulate or solve or calculate with in order to make predictions about where this will be in that mathematical space that we construct. And that was, I couldn't believe it. I was like, maybe I've been wrong all these years about how boring kinematics was. And all it required was a change of perspective. Now, fortunately, it's not a change of perspective that makes me like chemistry, but it's a change of perspective that makes me think that kinematics might have more going on in it than what I originally thought. What do they cover in Physics 2? You're going to take it next semester. So I'm not sure which Physics 2 it is that you're talking about. Usually Physics 2, if you're talking about a college course, would be talking about this electromagnetism. If you're talking about Physics 2 in the space of AP Physics, open AP Physics 2 course at a glance, that would be this one. It starts with fluids and thermodynamics. This is actually the class that I teach next semester, except for us it's Physics 3, starting with fluids and doing thermodynamics, and then optics is usually what we go to after that. We don't do electric fields is our Physics 2. Optics and quantum and nuclear physics is what I covered. That's in the college class. This is Physics 2 for AP Physics, which we will get to hopefully not by the end of the summer, but probably by Christmas. I think we'll be into this kind of material. All right. So let's talk about how we do this. We will recall that I mentioned before that we live in a universe that has dimensions associated with it. Those dimensions have length. We see 3 large spatial dimensions that have units of meters in all those directions. We also have a unit of time that is important. Okay, so here's another question. What's the difference between college physics and AP physics? So AP physics is kind of a truncated version of college physics. You get college credit for it if you pass the exam, the AP exam, but it covers a lot of the same stuff, but it doesn't cover in quite the detail. So you have fewer days taking the class and slightly less material taking the class, basically is what it comes down to. They typically are from the same textbook. So when you do, if you like, all of the physics classes or all of the 4 different AP classes can be taught out of the same textbook. So it's just different chapters of the material. So when I do college physics, now another difference is that this particular, well, so I didn't take AP physics in high school, but a lot of AP physics is done using algebra-based calculations, where the class that I teach in college is did I say calculus-based? I meant algebra-based. So in high school and for pre-med students, it will be algebra-based, meaning that you don't have to have calculus to solve the problems. And the class that I take uses calculus in the derivations and in the calculations. So that's another difference, is what level of mathematics does one expect to be present. Calculus is the easier one to use, and so I will actually be using the language of calculus in a lot of this stuff simply because it's a more elegant way of formulating the results. Okay, so I mentioned before that you have, when you have a coordinate system, you have some kind of mathematical model, and you might be plotting different variables that an object can have. So here's an object right here. The object can have what? It can be spinning, so it can have some spin, it can have mass, it can exist in location, it can exist in some period of time, it could have whatever else. It could be color, it could be blue, so like color, like blue or green. All of these are different properties that a given object can have. And so you may be wondering, as you're doing a physical model of something, you may say, oh, how do these properties change with each other? So for example, you could imagine taking, if you don't believe me, so we'll change this to color. You could say, as I have an object right here, and I light a fire underneath it, so here's a fire, and it's heating this object up, I could wonder, how does color change with time? So then I could plot color on this axis, which would be basically the wavelength of light that it has, and you'd have time on this axis, and as I'm heating it up, the color might change from red, which is long wavelength or low energy light, up to blue or white once it gets hot enough and all the colors are mixed together. And you can say, oh, so here's how the color is going to change the way that we perceive it as a function of time. So any object is going to have a variety of properties. Those variety of properties are going to depend upon a whole bunch of different things. And when you have a mathematical model, what you're actually trying to do is predict, how does one thing change with respect to another. You want to have some description to constrain the motion of an object through some arbitrary space. So you have an arbitrary space. It could be, position here and time. So here's a space that has position and time. These don't have the same units, right? This is measured in seconds. This is measured in meters. And so you have this arbitrary space, and you say, I have a particle that exists in this space, and I want to constrain its motion along some trajectory. I want to understand how this particle is going to move along some trajectory in this space. So in this case, it's a space of position and time. It could be a space of energy and time. It could be a space of spin and time. It could be a space of position and velocity. So you can imagine having, I want to understand where an object is located as a function of the velocity that it has. And you constrain your particle to follow some path, or you want to understand how a particle moves in a path along in this space. So in my when a scientist or when a mathematician talks about a space, they're basically saying a coordinate system that maps a variety of variables into some mathematical structure that you can then use. All right, so this is what we're talking about. We're going to have a mathematical space that we want to use to understand some physical phenomenon. That mathematical space could be whatever variables we happen to care about, and then we're going to use our understanding of, we're going to try to understand different laws of nature that allow us to identify what path something will take. The path in principle could be arbitrary, but if there are physical laws that are governing the motion of something, then arbitrary is not really what you have. You have a constrained set of motions, families of trajectories that objects can take as they travel through this space that you happen to care about. So the space that is most common, especially in kinematics, it's a place where we start, is that you're going to typically map position as a function of time or velocity as a function of time or something like that. But we don't even know what position and velocity are. So let's start, first of all, with just position in general. So you have some number line. Okay, so you're basically saying, here's a position. I'm going to choose a coordinate system. I'm free to choose. I'm going to choose a coordinate system where, like, this is the point 0, and then I'm going to measure the movement or the displacement of an object on this coordinate system in either direction. Okay, and you map it out in some unit. So in this case, we're going to just go ahead and go with the units we have, but we talked about last time how these don't even have to be equidistant, right? You can have a coordinate system where the gaps between different locations on your coordinate system changes. Okay, so this might be a meter, and so we'll just go with it that it is a meter. So you have a thing laid out, meters in both of these directions, and you want to say, okay, here is a coordinate system. I'm going to impose my coordinate system. I'm going to impose my perspective on the universe, set it down here, and I'm going to have, you know, some object that I care about, like my dog. I don't have a dog, so I can draw a picture of an arbitrary dog. So here's a dog, and it is located at some position in this coordinate system that I put on the universe. And as long as I'm consistent with what the physical laws are and what my coordinate system is, then I should be able to, you know, get the motion of this dog as it, you know, runs through the neighborhood or whatever. Okay, so making this map, this is an example of how you take a physical reality, you construct a mathematical framework, you construct the coordinate system, and then you place that coordinate system on the physical reality, and you map the positions. You connect the position that you observe with a location in this mathematical space that in this case it'll be the x-axis, but it's going to be the position axis in some direction. Now, a few other things to consider when we're talking about these positions. So going back to the idea that you can have a coordinate system that actually changes with time, I thought about this a little bit earlier as well. So suppose that you are looking at a map. So here is this person right here, and you're looking down at the top of the person's head. So pretend that you're looking at the top of the person's head. And the person is moving from one location to another like this, okay? And so we are imposing our coordinate system on the surface, on this guy right here, and there is the positions. And so we watch the person move, and it may be that the person is moving along, and he starts kind of fast, and then he slows. So he's like fast here, and then he goes slow, and then he goes fast again, and then he goes slow again, and et cetera, and so forth. So like his speed, the speed that he's moving, even though I haven't talked about speed yet, but let's pretend that we understand what it means, that his speed starts high, and then it goes low, and then it goes high again, then it goes low again, and then he comes out on the other side. So what could be causing him to change? And what could be causing this change? Well, one thing could be that he's just not moving the same. And then, but consider this. What if you look from the side, so this is looking down at the top of his head instead of from the side. Now let's pretend that we're actually looking from the side, and we see something that looks like this. Okay, and so now this person is walking along like this, walks up here, walks across this way, walks across this way. It may be that this person is actually moving at a constant speed, like he's passing 1 meter all the way along, 1 meter at a time, 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 like this. But from our perspective, looking down at the top, we don't see the fact that he's actually going over a hill. We just see that he's moving along here, and that he slows down. The person slows down right there, and it could be a she. She's hike all the time as well. So the person would be going at some speed here, going slower as they climb, not because they're actually physically moving slower along the surface, but rather because the surface is distorted. The surface has some curvature to it. Whoa, I just messed up. Oh my gosh. One of these days I'm going to figure out how to use this drawing pad, but that's not today. So somehow magically I rotated my reference frame. But anyways, so the person could be moving at a constant speed the whole time, but from our perspective up here, from this different point of view, it's no longer moving at a constant speed. Now, please excuse me for a moment as I close this and I reopen it because of my incapacity at using my drawing pad. After 4 years of using this drawing pad, I still don't know how it works. Okay, so you have this, and that basically is a distortion in the coordinate system. That's a curved coordinate system. And so you can make a map or make a mathematical function that says once you've moved to a certain point, you can describe the curvature at that point or how much that point gets distorted. So what you would typically say is, here's some coordinate system that I have. Here's the top-down coordinate system, and it looks like this. And then I'm going to say, okay, if this is 0, then you'd say maybe at position 3, there's actually some function where when I get to position 3, it actually corresponds to some other value that is a map between this top-down coordinate system and this side-to-side coordinate system, the one that's looking here. So, when this one, if you map just straight down, it actually corresponds to a larger distance when the slope is kind of steep. So anyways, there's all these kinds of things that could be going on. Now, from the outside perspective, we haven't got to this yet, but from the outside perspective, if this is our coordinate system and we are claiming that these things are all equidistant from each other, and that's the perspective that we're using, what we would say is happening to the person walking along this curved surface is that, there's a force being exerted on this person, and that force is causing them to slow down. And then there's another force acting on them that's causing them to speed up, and then there's another force that's acting on them that's causing them to slow down. And it's related to, this surface field that they're going through. So we'll get into more details about that and what it actually means to be a force. But just the point being that coordinate systems are somewhat arbitrary. We choose what they are. And we scientists and humanity have adopted a standard, which is, these coordinates are have spatial units, and they're measured in meters, and a meter is a given size. And we're going to assume that everything is flat, that we're not working on a curved surface, that we're working on a flat surface. And so that's the coordinate system. At least we simplify all the problems to start with so that these kinds of things don't exist. Another thing that I didn't mention last time, but I might as well mention it now as long as we're talking about coordinate systems, is that the lie you've been told for your whole life that the angles of a triangle add up to 180 degrees. So here's a triangle, all of these three angles, the sum equals 180 degrees, which is only true in a very, very unique circumstances that is almost never realized in the real universe. So the assumption that goes into this is that, well, there's an assumption that goes into it. Let's explore what the consequences of this assumption are if the assumption is actually violated. So if you were to go out into a parking lot and you were to stake down 3 different pegs in the parking lot's perfectly flat. It was just resurfaced by the facilities people. So now you have a perfectly flat, smooth parking lot. The water will pool uniformly across the surface of the parking lot. And you were to put down 3 stakes, and you were to tie a rope around all these 3 stakes, and then you were to measure the angle. So you get far away from where the rope bends, so you don't have to worry about the structure of the rope. You get far enough out here, and you say, what are the angles? What do they all add up to be? And it turns out that the angles in this triangle are greater than 180 degrees. And the bigger the triangle gets, the more greater the angles add to be, to the point where eventually you take one thing to the North Pole, and this is a thing that I use quite often. You take one peg to the North Pole, you run another one down to Quito, Ecuador, and another one over to Nairobi, Kenya, that are both on the equator. So here's the equator. And Quito, Ecuador, Nairobi, Kenya, you have this thing. This line of longitude right here will land right there. There's a 90-degree angle there between the line of longitude and the equator. There's a 90-degree angle right here. That right there is 180 degrees. And then you still have this angle up here. Okay, so the sum of the angles is more than 180 degrees. And it depends upon how big your triangle is, what's the length of your sides, compared to the radius of the surface, the radius of curvature of the surface. And only when the radius of curvature of the surface is infinite do you get a flat plane. So now you have a flat plane, and when you have a flat plane, then the sum of the angles of the triangle add up to 180 degrees. If you have a curved plane like this, it looks like a kid with a baseball cap. If you have a curved surface like this, then the angles are going to add up to more than 180 degrees. If you have a flat surface, it'll add up to exactly 180 degrees. And so that's the geometry that we use, this Euclidean geometry. If you have a saddle, so a saddle that looks kind of like this, then the angles of a triangle on a saddle will tend to be less than 180 degrees. Okay, so a triangle drawn on a saddle, the shortest line connecting 2 points on a saddle are going to curve in such a way that the triangles look like this. So we've all been lied to But we've been lied to with good reason. As one of them is that this kind of geometry is a bit more complex to manipulate and to visualize than this geometry, and so that's the geometry that we teach our children. If the standard we use is Euclidean geometry, what is its counterpart? So the counterpart, it's just called non-Euclidean geometry. So this is Euclidean geometry, which is Euclid and Euclid's postulates is right here, and non-Euclidean geometry is when you have curvature. Now, one thing about Euclidean geometry, as long as we're taking we're deviating slightly from into this tangent. With Euclidean geometry, there are 5 assumptions that go into geometry, and all the rest of geometry is based upon those 5 assumptions. One of the assumptions is like all right angles are congruent to each other. So all right angles are congruent. Another one is there's 4 of them. I guess we might as well look these up just so that we have a record of what we're talking about. But there's a 5th postulate that's important. Euclid, what do they call them? Postulates? Euclid's postulates from Wolfram Math World. A straight line segment can be drawn joining any 2 points. Okay, so far so good. You take 2 points, you can draw a straight line segment between those 2 points. Okay, a straight line segment can be extended indefinitely in a straight line. Any straight line segment you can take and you can extend it indefinitely in a straight line. Given a straight line segment, a circle, given any straight line segment, a circle can be drawn having the segment as radius and one endpoint as the center. And number 4, all right angles are congruent. The rest of geometry comes from those 4 postulates, with one exception. There's a 5th postulate. Okay, so these 4 things: a straight line segment can straight line segment can be drawn joining any 2 points. If you take a straight line segment, you can extend it indefinitely, and it will remain straight. You start with a straight line segment, and you pin down one side. You can draw a circle with that. So the circle is the locus of points that are equidistant from a given point. And all right angles are congruent. Hey, thank you for that raid. I appreciate that very much. 79 people. Welcome aboard. So we are, for those who are new, my name is Jason Steffen. I am a physics professor at the University of Nevada, Las Vegas, and we are exploring the deep, dark secrets of physics, especially high school physics, the way that high school physics should have been taught, at least the way that I would have appreciated having been taught instead of the way that it was taught for me. So we're going to be doing some pretty cool stuff I'm looking forward to today. All right, now this 5th one, all right angles are congruent, that is called so that's the 4 postulates. This 5th one is called the parallel postulate. And ignore all the text down here because it's stealing my thunder. I want me to be the one that appears smart, not the website that I'm reading from. Okay, so the 5th postulate is if 2 lines are drawn which intersect at a third in such a way that the sum of the inner angles of one side is less than the 2 right angles, then the 2 lines inevitably must intersect at sides far enough, etc., blah, blah, blah. So that's the parallel postulate. What this one is saying is if you take another way of formulating it, there's a variety of different ways of formulating it, is if you take a line and a point that's not on the line, there's exactly one line that you can draw that will never, where the 2 lines will never intersect each other. So that's another formulation of the parallel postulate. This one says if 2 lines are drawn which intersect a third in such a way that the sum of the inner angles on one side is less than 2 right angles, so that, if I were to redraw that, that would look like this. So now you have the sum of this angle and the sum of this angle are less than 2 right angles. Then the 2 lines must inevitably intersect each other. And so then you come back here and you say, well, there's a point of intersection. Okay. This postulate is equivalent to what is known as the parallel postulate, which is the one that I gave. Okay, so these 2 things are equivalent. Whoops, I didn't mean for that to happen. I think what happens is my touchpad, my pad is sensitive at different locations, and if you touch it in secret spots, it will magically cause things to happen on the screen that you did not ask it to do. Okay, so that's the parallel postulate. The 5th postulate here, this 5th one, cannot be proven as a theorem from these first 4. And it turns out with good reason, because it only works when you're working on a plane. The parallel postulate, the idea that 2 parallel lines will never intersect, only work on a plane. If you have a curved surface, like on a sphere, parallel lines on a sphere, so basically here you have 2 points. You can draw a straight line along those 2 points. That's the great circle, not the great pumpkin, but the great circle right there connects those 2 lines. that is this one. A straight line segment can be drawn joining any 2 points that are connected. You can draw a circle. So that's the first postulate right there, the fact that I can connect. A line segment can be drawn connecting any 2 points. That line segment can be extended indefinitely in a straight line. So the definition of a straight line on a curved surface follows the curvature of the surface, and it would go all the way around the Earth, around the backside, and it would connect here. So you get that indefinite length. Given a straight line segment, now a straight line segment, in this case, a straight is one, meaning that it follows the shortest path. Straight line meaning the shortest distance between the 2 points along the surface. That you can draw a circle in the following way. So you start here and you draw a circle and you would trace out something like that. So that's a circle right there. This radius is longer than 2 pi times the circumference. Than the circumference over 2 pi. So now the circumference of a circle on a curved surface is not equal to 2 pi r. Okay, and it actually depends upon the size of the radius. So you can have a circle. You could start with a circle like at the North Pole. You could have a radius that goes way down here, and then you draw a circle like that around the South Pole. So here's the South Pole, here's the North Pole. You draw a circle around the South Pole where this huge radius that's like almost the size of the whole Earth, and the circumference of the circle that you draw is tiny. And so the circumference of the circle is actually going to be a function of the radius that you're drawing. So there's that one. The point being, you can still draw a circle though, so that doesn't change. Given a straight line segment in a circle, you can draw a circle with et cetera and so forth. Right angles are congruent. That's still true on this. Oh, I just learned something. Okay, so the command thing will make some changes that you may not have anticipated before. So all right angles on this surface are congruent because now you measure right angles right at the point of intersection between 2 straight lines. So here's a straight line, here's a straight line, this is going to be right angle, and all these right angles are going to be congruent. So when the line of longitude connects with Quito, Ecuador, you will get 90 degrees on all sides. That is still true. So all these postulates are still holding, except for this one, that drawing 2 lines that intersect a third in such a way that some of the et cetera and so forth, this is different. Because now, whenever you have 2 straight lines on a sphere, they always intersect, and they will always intersect in 2 locations. Okay, so whenever you have 2 straight lines on a sphere, they will always intersect. There's no parallel lines, or I should say parallel lines intersect in 2 locations. That's basically what that boils down to. So you have one line that goes like this, and you'll have a second line that goes like this, and they will meet at 2 locations. They could meet right next to each other, or they'll meet at the North and South Pole. You'll always have 2 locations where they meet. You can also have on the opposite curvature where you have like a saddle point, you can have parallel lines. You can have one line that goes like this, and you can have multiple lines that run up here that never intersect the first one. So if you have a negative curvature, so I think positive curvature is the sphere, negative curvature is the saddle point, then you still get right angles are congruent, you still get that you can draw a circle, you still get that, et cetera and so forth, but you don't get any parallel lines. Or that's not true. You can have multiple lines that are not explicitly parallel, but that don't intersect another line. So this 5th postulate here is not answered. Now Euclid had always tried to get away, somehow prove the 5th postulate from the other 4, and he was never able to. And so, so there you go. So non-Euclidean geometry is a discussion of what happens when you have a curved surface. Now back to where we were before in terms of how do you map the physical reality onto your coordinate system. So here's me. I'm going to project a coordinate system on the Earth. Here's the system that I want to understand. It's a person walking down the street, whatever the case may be. I'm going to say, oh, here's the coordinate system. This is what coordinate system I'm going to have, and it's going to be laid out in such a way that I'm going to have the origin be right here. I'm going to have positive be in this direction because I'm the one that gets to choose. It's my model. I get to choose, but I can choose my coordinate system, but I can't choose the consequences of my coordinate system. Once I choose a coordinate system, the universe is going to do its thing, and my model has to match what the universe does. It doesn't matter how I describe it, as long as my model reproduces what actually takes place. Okay, and the description that I have of my model is, here's the origin, this is going to be the negative direction, this is going to be the positive direction. Of course, I could switch those. I could have this be the positive direction and this be the negative direction. It doesn't matter because it is, that is just how I am mapping the physical reality of this person standing here onto my choice of coordinate system. Okay. In this case, you have, it's going to have this person at some position. And what we're looking for, or what we're looking at in this particular chapter, and it's actually the next two chapters. It's chapters, 2 and 3. It's kinematics. And so kinematics is the mapping process of taking the world and putting it onto your coordinate system. And displacement is one of the things that you would care about. Displacement is not so much where is something located, on the coordinate system, but rather if that person moves somewhere else, how far has it moved? Okay, got a question. Speaking of curving, I've got a relativity question. How does it work with moving charges? A stationary observer would notice that a moving charge generates a magnetic field, but the same inertial frame, the charge would say that it doesn't generate a magnetic field. If you shot a test particle to have its path. Okay, so there, Yang Sunny, there is a great question, a great video that exactly addresses that thing by, it's Science Asylum. Well, where he does exactly that. I can't get into it here because I need to brush up on exactly how that works. Let's go back to this. All right. So we have a coordinate system. Here it is. It's laid out, and my objects are going to move around in this space that I've defined. And so here's where I start, or the person starts. Here's where the person ends. I've chosen, here is my origin. And so I want to find this displacement. Okay? And so that displacement, what you do is you take the final position, final, minus the initial position, initial. So final minus initial, you subtract the two, and that gives you the displacement. It's the difference between the two locations on a coordinate system. And so there you go. When something moves, the thing that everyone has to agree upon is this motion. So if a person moves from here to here, everyone in the whole universe has to agree on this distance that they have traveled. Okay? And that could be, you choose that your origin is located here, and you map on to this location and this location, and then you subtract the final from the initial, or you subtract the initial from the final. It's always x final minus x initial in this case, if this is the x direction. I could choose it to be a different direction. I could call it the tree direction. So I'm going to call this the tree direction because there's a tree in the distance. And so it would be tree final minus tree initial would be how I calculate this displacement. So displacement is something that everyone has to agree upon. So for example, suppose that the guy sitting next to me, who I will not be copying off of on the test because he could be doing it wrong, suppose that he says, my origin is actually going to be located here because this is where I live. So this is my house, this is your house, we don't live in the same place, and therefore my origin is at a different location. When your object moves from one position to another, you both will agree on the displacement. You won't agree on the coordinates, but you will agree on the displacement because that is the difference between the two locations. So that's why displacement is important, because that gives you the amount of motion that has taken place, and it immediately becomes independent of the coordinate system in the direction along that line. Suppose that you have someone else who comes along and says, I don't even like this coordinate system at all. I actually prefer a coordinate system that goes in this direction. And so my coordinate system is actually two different directions, like that. And now your displaced person is moving between these two locations. And I'm going to map that onto an initial position, which would be located here, and a final position, which is located here. Okay, so now I have another person is coming in, because their head is tilted sideways because they hurt their neck that morning. And so they're like, this is the coordinate system that I want to use. And I'm going to define my origin over here, which is not where this person lives or that person lives. And so this is where that person or the object starts. This is where the object ends. And I'm going to map it onto a new coordinate system where it's one direction like this and another direction like that. They have a warped worldview, but still the displacement that they get, that distance, has to be the same. So how are they going to get that displacement? Well, they've divided their universe up into two coordinates that are perpendicular to each other. And the reason you want them perpendicular to each other is, as we described before, that motion in one direction is completely independent of motion in a different direction. So that's the convention that we've adopted. It isn't always the case, as we showed last time, but it is what is primarily, it's usually preferred, especially in these kinds of problems, that your two directions are completely independent of each other so that you can just subtract one direction from another and not have to worry about it. Okay, so displacement is where's its final position, you subtract where its initial position, and you'll get this value, and all three coordinate systems will agree on what that distance is, what the displacement is between them. Okay, so in this case, you would have an xy, x initial, y initial, and then you have an x final and a y final, and then you subtract the final from the, or you subtract the initial from the final, just like this, except that now it's a two-dimensional thing, and then you want to get this distance, and assuming that it's a flat, that we live in a flat universe, or that your coordinate system doesn't have any curvature in it, then the sum of x squared plus the displacement in x and the displacement in y, so dx squared and dy squared, is going to be dr squared, because this adds up to, this is a right triangle, and the hypotenuse is the sum of the square of the two sides. And then you can calculate that displacement, and this will be the same as that person's coordinate system and this person's coordinate system. So that's what physics is actually invariant. You can choose your coordinate system, but when things happen, when the universe takes place and stuff goes on, everyone will agree on what the result is in the case of these displacements. And in this case, assuming that all the coordinate systems don't have any weirdness associated with them. So the conventional coordinate systems that we would adopt. So this is what kinematics does, is it takes reality and maps it onto things. Now, if an object is moving in a position with time, then you're looking at something else. You would have now you make a new space. Here's the space that I'm concerned about. I want position as a function of time. And where before we were looking at just, here's the position where it starts and where it ends, and then it started here and ended there, and you get this displacement. We may wonder, like, how did it actually get from one place to another? How long did it take? Did it just appear there magically? Probably not, because magic is what they do in a different part of Las Vegas. But it could have wiggled back and forth and then arrived there. There's all sorts of things that it could have taken place. And so if we want to map what happened, we want to have a more sophisticated model about what happened, not just the displacement, but also include the trajectory that it took to get there, then we would map it out as a function of time. We would lay out another coordinate system and observe the evolution of one coordinate with respect to a different coordinate, in this case time. And we would assume that, typically speaking, we would assume that time is always marching forward, that we start a clock and then the clock stops moving. And so then we could look at this displacement and say, oh, it starts at some location, it moves up, it moves down, it moves up, it moves down, it goes and gets its friend from its other friend's house, and then it ends here. The displacement is still, like the final displacement is still the final position minus the initial position. So that is this distance right here. That's still the displacement. But the trajectory that it took wanders through this multi-dimensional space that has two different coordinates. Something to be aware of. All right, now we have a two-dimensional graph of the motion of something, and graphs are interesting things because, as we learned from our algebra class, things have slopes. There could be some slope associated with this. You have an area under the curve, which in this case doesn't really mean anything important, but but it's there, and it might mean something important in some other parameter space, or it does mean something. Position times time does mean something, but not something that's particularly useful. As opposed to, you may have used a different coordinate here. It might be x and y, in which case the product of those two would give you an actual physical area. Okay, so in this case, the coordinates x and t, they don't have any special relationship when you multiply the two together. Well, that's not true either, because, wait, is that true? It's x and p. Yeah, so there's no particularly interesting relationship between x and t that you would multiply them together to get some quantity. Anyway, we'll get to that later. Okay, so the slope does mean something, however. That is, how much does the position change with respect to time? As time goes along, does this position change in some unique way? And so we have another quantity for that, which is how much does the x position change with time, dv dt, or dx dt, and we call this a velocity. So the velocity. something to consider when we have all these different coordinates is that we're going to have a mathematical model that is going to be, some function, whatever it is that we care about. It might be the position. So in that case, position would be x, as a function of other variables. Okay? And so it'd be like x as a function of time. It could be x as a function of velocity. It could be, that would be kind of unusual, but it could happen. It could be x as a function of y. You have some constraint that you care about in these different directions. It could be x as a function of t and y and spin and whatever. You could have a whole bunch of things. One of the differences, you might choose carefully which of these things you care about. One of the reasons that we use time a lot is because time is something that in our mathematical model always marches forward at exactly the same rate. When we get to relativity, we might change that perception, but for the first 30 chapters, we assume that time is always marching forward at the same rate, and so it's an independent variable. It doesn't care what the rest of us think. It's going to move forward, and so we will make our function on something that is kind of a stable foundation, so to speak. So we are going to have, this is what our mathematical model does. It takes a set of coordinates in this mathematical space that we've constructed, and it manipulates those coordinates based upon physical laws, and then returns a value also in that same space. Okay, so when we have, if we want to talk about velocity, velocity is going to be the rate of change of position with respect to time. Okay, and it's going to care about, for example, which direction that position is changing. So you can have a displacement. So this dx is a displacement. That's a minuscule displacement. You can have a displacement in a given direction. So if it's t final minus t initial, you'll get a displacement that looks like this. If this is final and this is initial. So you get a displacement that looks like that. And if that is changing with time, then you get a velocity that also points in the same direction. Okay, so time ticks forward, space ticks forward, and the displacement is positive, and the velocity is also going to be positive. So the fact that these things have signs associated with them, that the displacement can be positive or negative, or the velocity can be positive or negative, means that they are not just a number. They are, in fact, a vector. And the vector, okay, let me go back. That's actually not really the best way to describe it. In a given direction, it's got it's a signed number, and in that case, it is a scalar. So in the x direction, it's a scalar. It's just so a scalar to a physicist is just a number. However, the fact that we live in 3 spatial dimensions, so there's a spatial dimension in this direction, there's a spatial dimension in this direction, and a spatial dimension in this direction. Each of those things are independent of each other because we chose a coordinate system where they're all right angles from each other. So each of these directions is independent of each other. So if an object is going to move in 3 spatial dimensions such a way that its motion in every given direction is independent of its motion in all other directions, then we need to keep track of which displacement we're talking about. We might be talking about displacement in the x direction, we might be talking about displacement in the y direction, we might be talking about displacement in the z direction. Z is usually up. Why is it only 3 dimensions and not 4? In terms of, well, so time is a dimension, but it's a different kind of dimension. Time adds differently to this system. So the fact that you have 3 different displacements that you have to keep track of means that the way to keep track of them is that you order them. You choose an order, x, y, and z. And you have your space mapped out so that all these things have a very specific order. When these things are laid out in a specific order, it is no longer a single scalar. This is a scalar, that is a scalar, meaning just a number. That's a number, that's a number, that's a number, meaning that these are all coordinates. The x thing is a coordinate, the y thing is a coordinate, the z thing is a coordinate. But now they are in a specific order, and this whole structure, where they have a specific order that you do not change, now you've added constraints on your mathematical model, that these things do not change. That way you can translate between one person's coordinate system and another person's coordinate system. This is called a vector. So a vector is a series of numbers that are associated with specific coordinates that are ordered in a particular direction so that you can have a mathematical model that is self-consistent. Okay, and so now it points in a given direction. It points in a direction, in this case, associated with these 3 spatial directions. However, a vector can also have other things associated with it. You could have, we typically think about vectors as being, I'm in a spatial coordinate system, and here's my vector pointing in a given direction, and it has a length, and that length is a magnitude. And I can find that magnitude by summing the squares of the components of the different sides and adding them all together. But a vector, you can have x and t, your model be a function of position and time, this is also a vector, because now you've chosen these two things and you put them in a specific order. And now the time dimension doesn't have the same units as the spatial direction. And so the length here is a little bit different. So it really only makes, some of the things that they talk about with vectors only make sense. Some of the things that you will be told about vectors only make sense when all of the components of the vectors have the same units. In terms of like, it corresponds to a length, and that length means something special. It means something special in XYZ space because X, Y, and Z all have units of meters, or all have units of length. Okay, so that's basically kinematics. When you talk about a vector, it's going to have some magnitude and some direction associated with it. What did we got? Oh, all right. So velocity. You're moving along. Some position is a function of time. You're going to have a slope associated with that motion. That slope is going to give you a velocity. That velocity can change from one instant to the next, and so typically you would have, a velocity can follow some curve. But then you can also say, all right, well, what if the velocity changes with time? What if I have, instead of having my position changing with time, so that this quantity here is not zero, so I have a velocity and that's going to be this quantity. But what if I care about velocity changing with time, dv dt? Well, I can assign that a new variable. I'm going to call that one acceleration. So an acceleration is a change in velocity with respect to time. But what if I have dA dt? Okay, so dA dt, that actually has a name. That's a change in acceleration with respect to time. That's called a jerk. Okay, and then, well, what if I have, so we'll call it J. J is dA dt. Well, what if I care about the changing jerk with respect to time? And that's got a name too, and that's called, what, the yank or something like that, or the yoink. And then what if I have a d yoink d time, and then that's going to be called something else? I could do this forever. I could, the changing something with respect to time, which is a changing something else with respect to time, and I can work all the way back. This can go, you can have turtles all the way down. You can do this forever. But we stop at some location. We typically stop right here with these two. So we have position, we have velocity, and we have an acceleration. And we stop there. And in particular, we stop here with position and velocity. And this comes in from a different place. We don't think of accelerations. We think that accelerations basically cause a changing velocity with respect to time. But this is actually where the mathematics, or where the physics comes in, is right here with the acceleration. So I've never heard anyone seriously talk about the jerk as something that's important. Maybe engineers do every once in a while, and the yoink and the whatever else they call these higher, this trick repeated over and over again. Accelerations are the thing that are actually important. Okay, and that will come up in a later chapter, specifically when we talk about Newton's laws. So far, everything that we've covered, let me come back to this. All right, we've got this, we got falling objects, we got things like that. So when we talk about, now we have this mathematical model, we put these, we can measure the displacement, we can measure the position, we can see how the position changes with time, we understand the relationship between position and velocity and how they can translate into each other. But we haven't yet talked about what causes things to move and how, like, what the universe does to things to make them go from one place to another. So far we talked about like the magical appearance and disappearance of an object moving from one place to another, or the magic that it had in following some trajectory in this space and getting from one place to another. But we haven't talked about what it is, what that magic is, what's driving it. And it turns out that in the next chapter, forces drive things. It's forces that cause accelerations. And that is where the physics, like our understanding of laws of physics, translate into the mathematical coordinate system that we've adopted. So kinematics is just the coordinate system. It's how do you just map something onto a coordinate system? What if you have an acceleration, and then that tells us how the velocity changes, and the velocity changes tells us how the position changes. That is all just the mathematical formalism, the mathematical framework that we study things. What happens now is that we're going to say, there are forces that exist in nature, and forces cause things to happen. Forces actually cause objects with mass to accelerate. And that is what So this is where physics comes in, is on the acceleration. So our physical laws tell us about the acceleration, and then that in turn translates into our coordinate system, into our our mathematical structure. And so everything up to this point has just been math. It hasn't really been physics. The physics comes in when you add forces to the mix and gain some understanding and study how those forces cause things to move around in this mathematical space that we've put together. So that will be actually what we cover next time is, where did my thing go? Right here. All right, is there anything that we need to talk about with acceleration, things moving in a single direction? I don't really think so. That's the basics of what's going on. Projectile motion. So projectile motion is just saying, okay, now that I have this relationship between an object's position and an object's velocity, so in 2 dimensions, for example, or like even in a single dimension, I'm going to have an object that gets dropped, and it's going to have some acceleration. So here the acceleration is going to be equal to minus g. If plus is up and minus is down, then the acceleration is going to be equal to minus g. And now I can use the fact that I know that acceleration is the change in velocity with respect to time, and that the velocity is the change in position with respect to time. I can construct a mathematical equation that just maps the coordinate system onto this. I can say, oh, well, the position is now going to be acceleration, one half acceleration times time squared, because I can do the math that it takes to get this, plus the initial velocity times plus the initial velocity times time plus the initial position. And now I have a function of time that will tell me where my position is located, or is going to be given these inputs. So now I put minus g into this location. Maybe I don't have an initial velocity, so that term is 0. Maybe I don't have an initial position, so this term is also 0. Or maybe I do have an initial position because I'm switching from a coordinate system where this is equal to 0 to a coordinate system where this is equal to 0. Or maybe maybe sea level is now 0, but maybe the bottom of the ocean is now 0. So once you change a coordinate system, then all that does is manipulate these things. Okay, when you change a coordinate system, you're changing the location, the initial location of something. But what you care about in the end is the displacement, which is the difference between your final position and your initial position. And so you're kind of subtracting that over to the other side. So you can have coordinate systems. This actually shows you that you can have coordinate systems where not only the origin is different from one person to another, but the relative velocity is different from one person to another. So you could have a coordinate system where rather than having 0 be the top of the cliff, you can have 0 be at sea level. So that changes the coordinate system, but it won't change the displacement, because in the end, you're going to find out what's the difference between where you're located and where you started. When it comes to velocity, maybe you're starting off, you have a drone that's moving upwards with some speed, and so it's got a different reference frame for what it means to have an initial velocity. So, and this is actually something that's particularly interesting, is that's where you stop. You stop with something having a position and an initial velocity. The initial velocity and the initial position are how you actually define a coordinate system in the universe that we live in, where we use Newton's laws to describe the motion of something. So in Newton's mechanics, or in Newton's formulation of physics, which is the physics that we use for basically everything, you can specify, your coordinate system can be specified by an initial position, like the origin, and the motion that you can choose a motion for your coordinate system as long as it's a constant velocity. Once an acceleration comes in, that's a force, and that is a different term. So these two things define an inertial reference frame. And we will start at that point next time, is this inertial reference frame thing. Okay, does anybody have any questions? Let's see. Does time only travel forward? Shouldn't it be able to travel in every direction? So time travels in its own direction. Okay, hold on, let's see. Gravity, in my opinion, is a side effect of space-time curvature. Yes, so gravity is fundamentally an effect of space-time curvature, but if we impose this Cartesian coordinate system onto the universe, then there is no space-time curvature. There's only forces that cause motion through that space-time. And so what is space-time curvature in the realm of Einstein's theory is a force in the realm of Newton's theory. Does time only travel forward? Shouldn't it be able to travel in every direction? Time can travel in every direction, right? A time coordinate is just at what point in time does something happen, and you can say, well, I want to tell time based upon the Julian calendar instead of the Gregorian calendar, and so you can make a transformation in the time coordinate for one thing. In terms of like moving backwards in time, that is not quite as straightforward as it might sound. So you have an issue with entropy, and there are a lot of people who kind of think about these things in some great detail. That the arrow of time is always moving in a particular direction because the entropy of the universe is changing. I don't totally buy into those arguments, but I'm willing to talk to someone who does to find out what kind of holes I might be missing. But it turns out that not everything always moves, that the time coordinate can actually not run backwards in some interactions. So you can have violation of time reversal symmetry. That's kind of important. So time slows down when the mass of an object increases. For example, if you're orbiting a black hole in your perspective, you have orbiting in 5 minutes from the perspective of someone way farther out. So that, again, is the fact that time slows down when you get in a gravitational field is your time doesn't slow down, but someone from the outside observing you will watch your clock slow down. So my time, I'm wearing a watch, I'm standing right next to my watch. I can fall into a black hole, my watch will still tick the way that I have always perceived it. Someone else observing my clock will see something different. So it really comes down to who is the one observing which clock on whose body. So if I jump into a black hole with my clock will tick forward, and I will not see any change in the time coordinate, at least until the point where the gravitational force is significantly different between my eyes and my clock. Someone from the outside observing my clock will see something different. But then the question is, okay, which coordinate frame or which reference frame are you talking about? Are you talking about the reference frame from the outside observer, or are you talking about the reference frame from the person who's falling in? Let's see. Sir Magnus, we just finished talking about basically kinematics for high school physics. So, and it was a learning experience for me because I hadn't fully appreciated it, and so I'm going to probably spend the next couple of years pondering deeply about this to come up with an even better explanation of what's going on. Good movie to recommend for physics, time, and time after all this I can think of. So for movies, I wouldn't go that way. I would take a look at the YouTube channel that I mentioned earlier, which is Science Asylum. He's got some good things on time. You can see people talking about time. Leonard Susskind has a bunch of lectures that he did at Stanford where he talks about like what does it mean for time to tick forward and stuff like that. There's co-moving coordinates and proper time in cosmology, but that's different. Yeah. Don't watch it to learn about time or physics. I think it's pure fiction. Oh, so now one thing about Interstellar is it was actually written by a cosmologist. It was written by Kip Thorne, or I think it was Kip Thorne that wrote it. He might have just advised on the subject. So Kip Thorne is someone who knows what he's talking about. And so they did try to include a lot of like real effects in it, but it is still a work of fiction. All right, if there's no more questions, then my plan is to be back on Tuesday, and we will cover at that point dynamics. And this is where I think things get really, really interesting. So I appreciate everybody's time. I hope that you found it worthwhile. This was, like I said, it was me kind of exploring this stuff about kinematics that I hadn't appreciated until just a couple hours ago. Yeah, go ahead about the vector stuff from earlier. Interstellar tried its best to be scientifically accurate. Magic in a different part of the tensor besides just a fancy way to define a matrix. So a tensor, okay, now this is something different that I probably should have clarified. When you're talking about a vector and when you're talking about a tensor, it's not just a series of numbers. And a tensor is not just an array of numbers. So I guess that was something that was incorrect with what I said before. A vector is not just a series of numbers. It's a series of numbers that when you do transformations to it, it transforms under certain rules. And a tensor is a set of numbers in an array, a two-dimensional array or a multi-dimensional array that transforms under a set of rules. And so the way the mathematicians describe it is they'll say a vector is something that transforms like a vector, and a tensor is something that transforms like a tensor. And so basically, you have this mathematical structure. You come up with a rule to make it transform from one coordinate system to another coordinate system. And if it preserves some property in that transformation, then you call it a vector or you call it a tensor. So that's basically what it is. So it's not just any set of numbers that will do it. It's a set of numbers that has specific relationships among the different parts that allow it to adhere to some kind of conservation when you do a transformation on it, something like that.